Alright, so now we want to prove Cauchy's theorem using Ceelo's theorem, even though we talked about Cauchy's theorem, or the book talks about Cauchy's theorem before it talks about Ceelo's theorem. And for things like this, you have to be really careful because, like, if you're proving Cauchy's theorem, you can't use something that's based on something that's based on something that's based on like if you're trying to use Ceelo's theorem to prove Cauchy's theorem, then in this proof we can't use anything that's based on something that's based on something, so on and so forth, that's based on something that's based on Cauchy's theorem. Because if that happens, then we have circular reasoning. And a lot of times, like if you're like if it's been a while since you proved something, like you proved something and then you've proved a whole bunch of results in between, and then you prove something else, and you want to prove that that new thing implies the old thing, then you have to like look back through every single all of the new stuff that you've produced and make sure that you haven't used the old theorem in these new tools that you have developed that you're trying to use to prove the old theorem. A common example of where this will be an issue, and you'll get this in calculus courses, where you're trying to prove the limit as x goes to 0 of sine x over x. And so what's a common thing to do? Oh, well, when x goes to 0, this is going to go to 0 over 0. So you use L'Hopital's rule to prove that this is, let's see here, the derivative of sine is cosine x, and the derivative of x is 1. So obviously this is just going to go to 1 over 1, which is 1. So here we've used L'Hopital, or there might be an S in there, I don't know. It's like, yeah, I think there is an S in there. S? Question mark? But anyways, this is actually circular arguing, because how do we prove that the derivative of sine x is cosine x? The way that we prove that so the derivative of sine x evaluated at x equals 0 is just the limit as h goes to 0 of sine 0 plus h minus sine 0 over h minus 0, which is the limit as h goes to 0 of sine h over h. And look, that's exactly what we're trying to prove here. So the way that the reason you know that the derivative of sine is cosine is because you've already done this exercise before, and you must have done it in a different way. Because you wouldn't have been able to use L'Hopital's rule here, because it's just circular. Turns out the way that you do this is you use the squeeze theorem. And that's why you're able to prove it really early on in calculus, because you don't need much to know the squeeze theorem. A lot of textbooks, I think, just say like, oh, you can use the squeeze theorem, it's a thing, even if they don't rigorously prove it, because typically in calculus you're not doing proof-based mathematics, at least the first time you see it. But yeah, so you have to, so I guess this isn't technically wrong because it technically does work. Like you technically can use L'Hopital's rule, and you use the fact that the derivative of sine x is cosine x, and it works, but you're sort of using circular logic here. And so it would be best to just use the squeeze theorem the way that you did when you were evaluating this limit in the first place, when you're figuring out what the derivative of sine is at 0. So yeah, when you're trying to prove, when you're trying to use the main point, and this turned into a much longer rant than I was anticipating, is that if you want to prove something old using something new, you have to be really, really careful. And I'm actually not 100% positive that the proof that I'm going to give right now doesn't somehow rely on Cauchy's theorem, but I really don't have the motivation to go through and make sure that there's no subtle thing that I've used that somehow relies on Cauchy's theorem. I don't think this is circular, but it might be. And I don't know how I would, like, if you want to actually prove that it's not circular, then you have to like trace all of your arguments, all your propositions back to a place where you know that you're not using Cauchy's theorem, and that can be really hard. But anyways, so let's do this problem. I claim that I claim that if the order of G is finite, i.e. G is a finite group, and P divides the order of G, and P is prime, then G contains an element of order P. So, given such a G, we can write the order of G as P to the alpha m, where obviously alpha is an integer which is greater than or equal to 1, and m does not divide P. Okay? Now, by Ceelo's theorem, I typically refer to like the Ceelo theorems because there's like a bunch of them, but I guess here we just Dummit and Foote like to just say Ceelo's theorem, but whatever. G has a subgroup, which we will call P, such that the order of P is equal to P to the alpha. Define a sequence inductively so P0 is going to be P, P1 is going to be the center of P, and for all natural numbers n. Now when I say natural numbers, I mean 1, 2, 3, and so on. So I don't include 0 in the natural numbers. So Pn is going to be the center of Pn minus 1. So of course we can't allow n to be 0 here. Okay, then obviously Pn is going to be a subgroup of Pn minus 1 for all n and n, since the center of a group is always a subgroup. And so considering that as a group in and of itself, its center is a subgroup. And so the order of Pn is going to be P to the alpha n, where alpha n is between 0 and alpha n minus 1. But we actually know more than that. Okay, come on, computer. In fact, since the center of any P group is non-trivial, and now this statement, the fact that the center of any P group is non-trivial, that I sort of need to go back and verify that does not rely on Cauchy's theorem. Because if it does rely on Cauchy's theorem, then this whole argument is circular. And based on the statement of the problem, like it very easily might be. I could imagine Cauchy's theorem being useful in proving that the center of any P group is non-trivial. But like, I'm not going to go back through the text and find it and read through the proof and see, oh, does any part of this rely on Cauchy's theorem, or look through any proposition or any theorem that's used in the proof of the statement and say, oh, does that rely on Cauchy's theorem? Because then you have to keep looking and everything. So I'm going to leave that up to you guys if you want to go back and make sure that this does not rely on Cauchy's theorem. The problem statement seemed to imply that you're unlikely to run into well, certainly you don't use Cauchy's theorem to prove the Ceelo theorems, but that doesn't mean that you don't use Cauchy's theorem to prove any other facts, such as this one, which is not... Well, is it part of Cauchy's theorem? I don't know. Whatever. In fact, since the center of any p group is non-trivial, 1 is less than alpha n is less than or equal to alpha n minus 1 for all n and n. All right? Since alpha, which is alpha 0, is finite, and Pn, the sequence, is countable, well, countably infinite. There must be some natural number n such that alpha n equals alpha n plus 1. And if you think about what's going on here, if alpha n equals alpha n plus 1, then, okay, so since, actually, let me say the next sentence and then I'll go back to what I was about to say. Since alpha n is alpha n plus 1, Pn equals Pn plus 1, and so Pn, or rather, maybe IE would be better. So Pn equals Pn plus 1, that's the same as saying Pn equals z to the zPn, and so Pn is abelian. Now, it should be obvious at this point that that pk is going to be equal to pn for all k greater than or equal to n, but I'm not going to write that out since that's not necessary for this problem. But that is something to keep in mind about the sequence that we've constructed. It's going to keep decreasing until it gets to a point where it just stabilizes. Okay, so Pn is abelian. Then Pn is, because it's abelian, it's just a cyclic group of order p to the alpha n, which means that, and now we're going to use some crazy superscripts here and subscripts, but it's really unavoidable, I think. So then Pn is the cyclic group generated by G, where G in G is an element of order p to the alpha n. Then G to the p to the alpha n minus 1 is in G is an element of order p, because the order of G is p to the alpha n, which implies G to the p to the alpha n, G to the p to the alpha n equals 1. So the so G to the p to the alpha n minus 1, if we raise this element to the power of p, then this is just going to give us G to the, we have p to the alpha n minus 1, and we're multiplying that by p, which is going to be G to the p to the alpha n, which is equal to 1. And so, of course, that means that G to the p to the alpha n minus 1 is an element of order p to the alpha n. Now, technically, this only implies that its order is less than or equal to Well, yeah, it's an element of order p because you raise it to the p and it gives you the element 1. And technically, this only this line of reasoning only implies that it has order less than or equal to p to the alpha, or no, that g to the p to the alpha n minus 1 has order less than or equal to p, but obviously since p to the alpha n is the order of g, you can't have anything, if you can't raise g to a power less, if you raise g to the p to the alpha n minus 1 to a power less than p, then you're raising g to the power of p to the alpha n. Well, you're raising g to a power less than p to the alpha n. And since p to the alpha n is the order of g, it's the lowest positive integer that will give you 1 when you raise g to its power. And so if you raise g to any lower power, you're not going to get 1. And so that proves that this isn't that the order of this element is p. So hence, g has an element of order p. And yeah, there we go. This is what we wanted to prove.